Okay, slightly trickier problem. Again, we're going to be deciding R and S, and now we have a molecule that looks like this. This is going to be one where both of the Kahn-Ingold-Prelog rules come into play, where you need to pay attention both to a highest atomic number and at the first point of difference, and so on. And let's go ahead and assign this. So first, where are the actual potential stereogenic centers in the molecule? Well, I hope you recognize immediately that the bromines are obviously potential stereogenic centers, and the other one that jumps out at me as potentially being a stereogenic center is this methyl. Now, which ones am I discounting immediately? Anything that has 2 hydrogens bound to it, I can safely ignore right away, or anything that has 3 hydrogens bound to it, like the methyl. Having said that, I should probably go ahead and draw the implicit hydrogens explicitly. So in other words, this methyl has a hydrogen lurking back behind it, and this bromine has a hydrogen lurking right here in front, and this bromine likewise has a hydrogen lurking here in front. Okay, so now let's go ahead and assign priorities. So let's start with this one arbitrarily. So priority 1 is going to be the bromine. Priority 4 is going to be this hydrogen. But now, and again, I'm trying to evaluate this carbon right there, I have a tie at first. So here we have a carbon, and this goes off to a carbon, and both of these carbons have 2 hydrogens bound, so we're tied so far. Okay, then we go to another carbon. Again, that's a tie so far, and this carbon has a bromine bound, so this direction wins because this carbon only has another carbon bound. Well, not counting the other carbon that they both have in common. So this one wins. So priority 1 is the bromine directly bound to this carbon. Priority 2 is in this direction, and priority 3 is in that direction. We could play the same game with this carbon-bromine bond. So the carbon-bromine is going to be 1, the H is going to be priority 4, and then you can walk through the same analysis, but here we're tied, carbon, hydrogen, hydrogen, and so on, and then we arrive at a bromine faster down this path, and whereas going this direction we arrive at a methyl. So priority 2 is going to be in this direction, priority 3 is going to be in that direction.
Okay, so this isn't the most important point or anything, so I'm not going to refilm the whole thing to fix it. But I regret the choices I made with the little notations that I was making here, so I'm going to go ahead and erase those, and let's try this again. So I'm trying to evaluate the red carbon, of course, and the analysis still holds. The bromine's going to be priority 1, and the hydrogen's going to be priority 4. But then when I'm examining these 2 carbons, it doesn't make sense for me to write down that they are both C. Instead, what it makes sense is for me to write down what they are also attached to. So when I go to write down what's attached to this carbon, I should write C, referring to this carbon right there, H, and H, because what we have is a carbon that's bound to another carbon and 2 hydrogens. Same analysis over here. This carbon is bound to this carbon plus the 2 implicit hydrogens. So this also I should just write down as CHH. Then, since I'm tied so far, we go on to the next one. And here, what I'm looking at is a carbon and a carbon, but if I'm analyzing this carbon is bound to 2 carbons as well as the implicit hydrogen, so I really should write this as CCH, whereas this carbon right here is bound to a carbon, a bromine, and a hydrogen. So this one really is BRCH. Obviously this is heavier and it wins over that. The exact same analysis can be done if instead what you are trying to do is evaluate this carbon instead, and then of course these would remain CHH, and then over here I would say that this is a bromine, carbon, hydrogen that are all bound to this carbon, so I would say BR, H, and C are all bound to that, whereas over here I would once again arrive at 2 carbons and a hydrogen bound going in this direction.
If we're evaluating this stereogenic center, then the methyl is not going to be priority 1 because methyl is relatively light. It is a carbon with 3 hydrogens bound to it. So I would say 3 hydrogens bound.
Here I just wanted to note that I implicitly changed my notation in the video and was doing something that's consistent with this system that I was using here. And so when I got to evaluating the methyl, I just simply said it is a carbon that has 3 hydrogens bound, and therefore I just simply wrote down the 3 H's that are bound to it. Again, if you're going to be systematic about things, I would recommend doing it the way I'm doing in this part of the video as opposed to what I was doing on the LIGHTboard.
And then, back behind, this is definitely going to be priority 4, so the question is, what should be priority 1? Well, if I'm looking at this carbon, then I'm tied there, CHH in both directions, and then I'm tied at the next one because it's a carbon and a bromine. So what happens is, I have a tie for 1 in both directions, then this is 3, and then that's 4. Said another way, is this a stereogenic center? It is is not, because you end up tied going off in those directions. So how many stereogenic centers does this molecule actually have? Well, only these two. This right here, I needed to evaluate as a stereogenic center, but it turns out it is not, in fact, a stereogenic center at all. So how many stereogenic centers in the molecule? Just two, the bromines, the carbons that have the bromines bound. All right, so let's assign R and S on each one. Unfortunately, in both cases, in order for me to assign them according to the normal rules, what I would need to do is to pick up the molecule and rotate it 180 degrees, so the H's would end up back. Now, to get this formally correct, of course, what I've done is I've taken this blue molecule and I've rotated it this way, 180 degrees, so that the methyl, which was up, is now back. And what I've also done then is I've made this orange priority bromine is now going to be this one. So using the orange marker for this bromine, again, would define the bromine itself as priority 1, the direction headed toward the other bromine as priority 2, the direction headed toward the methyl as priority 3, and the hydrogen as priority 4. And once I've done that, I can see that this is rotating in the counterclockwise direction, so this is going to end up as S. Likewise, if I am assigning priorities, this bromine is the one that was originally yellow, so I'm going to keep it yellow as well. Priority 1 in that direction, priority 2 is headed toward the other bromine, priority 3 is headed toward the methyl, priority 4 is headed toward the hydrogen, and so now what I have is this rotating clockwise, so this stereogenic center is R. Okay, once again, I learned that I'm not quite competent to teach all aspects of stereochemistry through the LIGHTboard setup. Sometimes I really do need to have the orientation where it is audience, me, and then the thing that we're examining together, and we're oriented in the same direction in order for this to work. So some aspects work just fine on the LIGHTboard, but specifically the right-hand trick does not. So the analysis that we've run so far basically says that if this bromine is priority 1, and going toward the other bromine is priority 2, and then going toward the methyl is priority 3, and the H is toward us 4, then we need to rotate the molecule in order to end up in the right sort of orientation to just simply read the stereochemistry off the screen as is. And so what that means is the axis of rotation that I'm going to use would basically start like this, and I'm going to rotate this way. So the carbon that's in blue here will end up over here. Again, I'm doing a 180-degree rotation around the vertical axis. And so the methyl, which is toward us, rotates around and ends up back into the board. So what that means is that this bromine, which is now priority 1 right there, priority 2 in this direction, priority 3 in that direction, priority 4 is coming toward us, that hydrogen. This red carbon, of course, ends up right there. And therefore, again, priority 1 is going to be here, 2 is toward the other bromine, 3 is toward the methyl, and H ends up back the way we need in order for it to be assigned well. And here we have priority 1, priority 2, priority 3, and priority 4. Alright, so if I'm going to do the assignments here, then the way to do the assignments is relatively straightforward since the hydrogens are pointed back in, so the priority 4 groups are pointed back into the board. So 1 to 2 to 3 right here, this is a counterclockwise sort of rotation. Therefore, the red carbon is S as drawn. This right here is a clockwise sort of rotation. Therefore, the blue carbon is R as drawn. And we should be able to complete that analysis likewise if we do it up here. But again, the whole point of this problem is that I can read it off easily as long as I've done the official rotation to put those groups back. But if I can use the right-hand trick instead, this will be much faster and I can analyze the original structure. So again, what I'm going to do is basically try to align my fingers 1 to 2 to 3, like so. So I'm curling my fingers 1 to 2 to 3 this way, and my thumb ends up pointed back into the board, which is where priority 4 group is. Therefore, this is R. My right hand is working because my thumb is aligned with the H. Here, I have the H again pointed back away, but now if I'm trying to get my fingers to curl around from 1 to 2 to 3 like this, my thumb ends up toward the camera, but the H is back in. Therefore, my right hand isn't working. Said another way, my left hand will work. I can curl my fingers from 1 to 2 to 3 like so. My left hand thumb points in, the H points in. Therefore, this is S. Again, R is right hand works, S is sinister, that means your left hand works. So, when I'm doing this analysis in the first place, I see 1 to 2 to 3. My fingers are curling this way. My thumb is coming toward the camera. Therefore, since it's aligned with the H, my right hand is working. This is a right-handed rotation. And that means that this one here, if my fingers are curling naturally 1 to 2 to 3, my thumb is coming toward the camera, the H is coming toward the camera, therefore my left hand is working. And this is sinister. Or there is one more alternative have, and that is if your H is pointed officially back away, you get to use the R and S, read it off directly for clockwise and counterclockwise and so on. But the textbook does allow that if the H is explicitly toward you, then all you need to do is flip the sign that you get when you read it off first. I don't prefer the book strategy. I vastly prefer the right-hand strategy. Whether you use the right hand and the left, the book, whatever you do, find something that's consistent, that you get right every time, and use that, whatever works for you.
And do lots and lots of practice problems so you can lock away the ability to do stereochemistry at a glance. And one of the beautiful things about stereochemistry is you can check your work. If you just simply draw it in ChemDraw and then go to show stereochemistry, it'll tell you what the stereochemistry of the various items are. I will note here that this small s does not mean that it's S. What that's telling you is that this is a stereogenic center, potential stereogenic center, that is not currently a stereogenic center. So capital letters means it's actually a stereogenic center, and this is how you assign it. And the small letters are, this is pro-S. It is not yet S, but it could become an S if you did something to disymmetrize the molecule elsewhere. It's pro-S, not yet S.